Research Lab project. We started it indeed in January this year, and what our aim is to answer the questions: do water nanostructures exist? And how do these water structures, or how does water capture information? And currently we are working with the following techniques: mirrors, NMR, conductivity, and pH, and we're aiming to extend this. The project team is mainly us two, Alexander Tournier, who is also director of the Homeopathic Research Institute, and myself, and we collaborate with Dr. Stefan Baumgartner, who is at the University of Bern, and Professor Zenko Vokos in Köln. The venue is in Heidelberg, in Germany, and it's a beautiful place. I can say things similar to Professor Huck. It's with a river and a nice view. Okay, so now on to the things I did at Firelight Research. I apologize that some of this work will be repeated from what I did last year, so some of you might have seen this work. So we know that there are many waters in the world, bottled waters, all kinds of devices, and we had the question, what functional effect do they actually have, because a lot of claims are there. So does it do something to agriculture, does it do something to health, and can we really find a way to differentiate these waters by functionality and provide advice to consumers by really matching certain waters to a specific situation, telling them when to use which water, because we believe not always one water is continuously good for you, and informing water providers, so people making devices or people bottling from a kind of source, how to bottle the water, how to store their water, and at least what the effects of these things are. And at the same time, we know that water is dynamic and open, so there's always this thing that you're looking for some stable property, but we also want water to be able to perform its function, which is continuously different in life. So the aim is to scientifically investigate the functional effects of water, to design a reproducible method to measure this water functionality, and to be able to explain why water behaves in a certain functional way, and to be able to inform consumers and providers. So I'll go through this in the whole journey. So the first step, what we did was to investigate the functional effect of one water activation device, and that was by evaluating tap water before going through the device, which is called control, and tap water after going through an activation device, which we call activated water. This is the device. These 4 activation devices were in the greenhouse. You can use one device, but this was really to provide a greenhouse with the water that was required to really fill the fields. The hypothesis of this activated water is that it improves the resilience, it has a good effect on health, it is open to natural rhythms, but undisturbed by unnatural rhythms, and it has these properties for a long time. It's stable. So after tapping, it stands there and it's still holding these capabilities. The devices are a black box, but we do know that there's nothing chemically explicitly added, and there's no electricity used. So we assume that the effect is of a physical nature. That's it. So we started with experiments to measure control and activated water effects on agriculture products. We did 5 years of biological observations in the open field, in a greenhouse. We looked at yield, growth, and quality. We looked at germination rate, shelf life tests, and we did some tests in the lab where we tested for stress of light and water stress. And we saw a lot of things, so the results were indicative, definitely, of the hypothesized functionality. However, these tests are very time-consuming, and external factors influence the results, such as the season, the weather, the soil condition, the diversity within the species, and it's complex. But if you choose to go for one thing, you definitely will find stuff here, but we were looking for a better method. So what we also did is to gather 5 years of data with UV-vis Raman, near-infrared spectroscopy, and delayed luminescence on all the produce that we had in all kinds of ways. You can see all kinds of setups, the Raman in the field, and we used near, and we used reflectance spectroscopy, and at the bottom right it's delayed luminescence. So all kinds of methods to try to find out subtle physical differences within the produce. And also here we found differences, but we really need more data and analysis to find some statistical significant conclusions. You must know this lab was more a renegade. It was privately funded. We had to go quick. Professor Tsenko will know. So it's go quick, find a lot of things, and but we did actually a lot for that. So, but it wasn't like go as far as publication. So. We also did experiments to measure differences between the control and activated water directly in the lab, such as diffusion of substances, for the one water versus the other, diffusion on filter paper, exclusion zone size, pH level, redox, conductivity. And also here we found that it was really difficult to measure some of these things and to perform this accurately when comparing really similar waters. So we kept on looking, and this is all the introduction towards aquaphotomics. Then we found and decided to start using the infrared spectroscopy with the aquaphotomics approach. We all know this, so I can skip it, but indeed you always have light, which is the first perturbation, and you can add extra perturbations to bring out certain properties of the biological system. We get the near spectrum, we can visualize in the aquagram, and with the WAMAX we can build the letters and the information, the words of the specific spectral pattern in relation to the specific system that you're looking at. So also this we all know, this is the molecular mirror, so water structures change according to the physical, the chemical and biological perturbations, and in our case we assume the perturbation is a physical perturbation because we don't add explicitly chemicals or biological items. So what we did, what we decided to do is to introduce perturbations deliberately to investigate the water. We wanted to probe, tickle, challenge the water to really measure the behavior and the reaction of the water and to overrule factors influencing the experiment. Because there's so much going on in the environment, we thought let's use an external factor, which is physical, to bring out how these waters react to these perturbations. And keep in mind, the hypothesis really determines the choice of perturbation, so you can do all kinds of experiments. We are also considering to do long-term measurements where we really want to see the differences over time in relation to the season. So this is we were looking now for some physical property in this way, but there's much more what can be observed. So the experimental design that you choose to use really determines what you can find. So go back to the hypothesis that we had for activated water, these three top ones, and we assume that the effective device is of a physical nature, and we wanted in this case to focus on the last property, that it is stable. So we wanted to find something that is reproducible. Based on these two aims, our first choice was to introduce the temperature perturbations. So our measurement protocol, we filtered first the water with an 0.2 micrometer filter, because we never know if the tap water maybe had some biological contamination, so we wanted to at least get rid of that before we started to measure the things we were looking for. Then we insert it in the cuvette with a temperature-controlled cuvette holder. It's a Peltier-controlled thing with a cooling, so it can moderate up and down. Then we cooled the water to 2 degrees. We waited for 8 minutes until it was stable, and we would increase the temperature stepwise to 50 degrees, and per step it was taking 4 minutes and 80 consecutive spectra in the upwards direction, and downwards we took 6 minutes because it takes longer and more consecutive spectra. The shutter of the halogen lamp that we used is close after every spectrum. And one spectrum is an average of 64 scans, and one scan has an integration time of 23 milliseconds. And one measurement, in this case, takes 3 hours. So it's a sample, we set it in, it goes automatically. We had automated everything and it goes. So this is the measurement setup. At the bottom you see the temperature controlled cuvette holder. This is the cuvette. Here you see the near spectrometer. We have a fiber optics based setup from Ocean Optics and the halogen lamp. And yeah, we always log the room temperature, the room humidity, and also the operator, because temperature and humidity might influence even if you control a lot inside. Okay, so the first experiments we did to check the stability during the day, the month, and the year, and we checked the stability for different tapping dates. Here you see the differences in the month, and always the day. It was always like morning and afternoon. We switched it, and these are the different tapping dates. Keep in mind this is 1 year later. Our results are visualized in acrograms. You know, we have raw spectra. Very small differences are probably relevant for us, so the high accuracy and stable measurement setup is required. And we process the spectra. I learned Sunday a lot, so we probably would like to do other things to the spectra. And then we calculate the acrograms at the 12 main weighing units, so the known ones. You can calculate for specific systems, your specific ones, but this is the most simple thing you can do. So here are some results. Here's control and activated water of the same tapping date. And you can see that there's always a difference between the control and activated. Control is red, activated is green. This is the average of the whole thing, so I will later zoom in to show you more details. And yeah, it's reproducible here. So even during the month, the same water, we see the same difference. Then we do a different tapping date. Also here we see this difference in behavior and reaction of control versus activated. For us actually this was, after doing 5 years of experiments, amazing to find such a reproducible result. Maybe you think, it's easy, but this was for us really nice to finally see something, because water is so special. Then we tried it on 9-month-old control and activated water, and even that had the same differences. So indicating that this effect and difference was stable over a long time. Which can also be measured. We always had in the background the ability to do subtle energy measurements. So it was always confirming also what we could make. Then we decided to do more experiments to see the effect of different incoming tap water, so not of a different tapping date, but a different tap, and the effects of certain components inside the device. So taking a component out and taking a component Y out, where Y is inside another component, so not directly touching. Here we show that other tap water had also similar results. We see that always there's also something happening here. Well, this is an indication that that tap water is independent of the result of the activation device. And then we compared the effect of water activation with and without component X. And yeah, here you see the same. If you have without X, you see it's similar like control, if you remember correctly. With X, it's similar to activated. So it seems that component X seems to play a major role in the earlier presented device effects. So it could mean that aquaphotomics could be an aid in device design if you find what your property is and try to compare it. So then here we have comparing the effect of water activation without this component Y, where Y is inside component X. And you can see without Y, the effect is similar to the normal activated one. And with Y, it's more similar to the old control. So it seems that component Y seems to play an opposite role in the earlier presented device effect. And we actually, based on this and based on the measurements we did afterwards by taking the component out, this was confirmed by the measurements that we can do in a different way. And yeah, so also this showed that it could aid in device design, and it showed actually that something that's inside and not touching water can have definitely maybe some kind of physical effect on the water. And it goes through the detail. So what does this all mean? Based on the current WAMEX assignment, which we now use, because this is what we have, but there are all kinds of other interpretations, this was where the change was happening, and it had to do something with the water surveyation shell. So, and there was always more in the activated water, or at least it was longer. So it has to do something with the functionality of the water. More active, more free electrons. So let's zoom into this different reaction. This is what the normal, this is what I just showed, this type of things, but this is the zoom out of one of these experiments. On the left you see control, and on the right you see activated. And here you can see in the different temperature steps that there's a difference. Okay, I'll zoom into that. Around 37 degrees, there is a dip for control, and activated seems to keep this longer, this relationship. We're looking now at the ratio between these three. Maybe it means that some kind of structure is held longer inside the system, and I would definitely be open to see how our physics colleagues think about maybe some coherent domain that has a higher temperature resistance to change or something. It would be interesting, but that's what we reproducibly found, and 37 degrees is also interesting. Yeah, and we can do more in-depth statistical analysis to find all these things, but I won't go into that. We heard a lot what you can do. And then you need to relate it to the functionality. So we went through the first few steps, but we want to confirm with reference data as well. And we did a lot of other tests also with this water. So here, well, the germination rate of this activated Asian salad was higher, so maybe more activity. The resistance to water stress of this activated Asian salad was also better. The number of rhizobia, which is representative of the synergy with the soil microbes, so more liveliness, was also higher with activated water. The growth under light stress was more for activated wheat seedlings, so also more resistance. And we had people drinking the water, actually a set of twins, and there was a positive effect on the delta coherence, and positive effect on the power frequency spectra. On the top you have the activated and above, yeah, and control. So here more coherence, less differences. More differences, more stability. Then there we showed more ATP in carrots. This is in 1 year in soil that got the water 1 year, 2 years, and 3 years. And so the longer the soil had this water, the better, the more ATP the carrot had. And here's just fresh versus old versus fresh carrots. And we saw different effects on soil composition over the years. Okay, so the conclusions are, we investigated all of these things. I'll skip this because I see the time. And so now our vision is to inform consumers and providers by watermarking waters with aquagrams. Okay, so we're nowhere yet there, but we would like to start this. Build a database, understanding and explaining the functionality and advising on stability and storage for these device company providers. And be able to match water to consumer. This would be possible maybe with measuring your own aquagram, knowing the water and match it. Yeah, when we have all these mobile systems. Then I'd like to say that our vision has been for a while, the International Aquaphotomics Society, to do all this, and So I would like to remind you to really stay after this session and join this, this setting up the first stage of the society, because we need as much people as possible to be there to really be able to establish society. So thank you very much for your attention, and I'm looking forward to collaborate. Also, Alex at the Water Research Lab, we are really open and interested to have people join and come by in our lab. And thank you.
Thank you very much for this colorful presentation. Any question?
Thank you, Everine.
Yeah.
So, 2 quick questions. On the slide 29, so you show the difference between control and the test group on the aquagram.
Yeah.
Is a dip. So how consistent is the result? Meaning, if you do it again, you expect to see the same difference?
Yeah, we expect to see, well, we saw the same difference. It may be sometimes at 38 degrees or 39.
But the trend is there.
But the trend is always there. This is really, yeah.
Okay, thank you. And on the slide 32, you mentioned about the germination.
Yeah.
Is higher.
Yeah.
How much higher?
Okay, this is like maybe 3 or 4 years ago, so I can't answer that question.
Okay, that's fine.
But
Thanks.
it was reproducible over, we repeated these experiments over months, so.
Are we talking about single-digit percentage, or it's like 100%, 200% more?
It was, well, it was significant, but
okay,
yeah, sorry.
That's okay, thank you.
I have to look back more data. Yeah, sorry.
One more quick question.
Can you repeat kindly the definition of activated water?
Yeah, so it's gone through this device, which when we were measuring it, is considered as a black box. But I can tell you, it's a geometry, and the water flows in, and there are some things hanging in there, and that's it. It falls through, and these things are hanging there. So it's tap water. It goes in, it flows through. It's not a specific, really. I'm not. I can't say everything, but it's a form. And water goes through, and there are some things, elements hanging there, which are not like minerals that you can really get stuff off.
Thank you very much. Thanks, Everine, again. I would like to invite our next presenter, Dr. Aquaphotomics.